Today we are going to start topic Cayley-Hamilton theorem. Cayley-Hamilton theorem. Statement of this Cayley-Hamilton theorem is every square matrix should be non-singular. Non-singular means the matrix whose determinant is non-zero satisfies its characteristic equation. Now, what do you mean by characteristic equation? If A is given matrix, A is given matrix, lambda is scalar, lambda is any scalar, and what is I? If I is identity matrix. If A matrix is of order 3 by 3, you have to select identity matrix also of order 3 by 3. If A matrix is of order 4 by 4, you have to select identity matrix of order 4 by 4. And you have to simplify A minus lambda I. And determinant of, you have to solve determinant of A minus lambda I equals to 0. As it is equation, so we have to equate this thing equals to 0. When you solve this determinant of A minus lambda I, what you will get? You will get characteristic equation of matrix A. Characteristic equation of given matrix, given square matrix A. So satisfy means when you solve this determinant, you will get an equation in terms of lambda. If A matrix is of order 3 by 3, you will get cubic equation. If A is of order 3 by 3, then you will get cubic equation in lambda. If given A matrix is of order 2 by 2, what you will get? You will get a quadratic equation. Quadratic equation in lambda. And if in question statement is verify Cayley-Hamilton theorem, means you have to satisfy that equation. Suppose it is in lambda, it is cubic in lambda. Then put in characteristic equation, put lambda equals to A. And if it is quadratic equation in lambda, put lambda equals to A. And on simplify it, you have to show that equals to right hand side of this equation. Right hand side is 0. As we are dealing with matrices, so it should be 0 matrix. And if it comes out to be 0 matrix, hence our Cayley-Hamilton theorem is verified. And sometimes also asked in question, verify Cayley-Hamilton theorem and find A inverse. For A inverse, in this cubic equation in lambda, suppose A is of 3 by 3 order, you have cubic equation in lambda, and you will put lambda equals to A. You will get cubic equation in A. To find A inverse, you have to multiply this cubic equation in A with A inverse, and Keep A inverse term on left hand side and take rest of the terms on right hand side, and substituting the values in right hand side, you will get the value of A. And if it is quadratic equation in lambda, then put lambda equals to A. You will get quadratic equation in A, and again multiply A inverse with this equation and keep A inverse term on left hand side and take rest of the terms on right hand side and put value of the terms in right hand side and solve, and you will get A inverse. Sometimes also asked in question like A raised to power 8, A raised to power 7 means some equation of power 8, and you have to convert it into linear equation. For that, we use characteristic equation. We force this equation in A as first equation, and with the help of that equation, you have to simplify a higher order equation to reduce it into linear equation. I will explain all of these things with the help of examples. With the help of some examples. Now we discuss some examples based on Cayley-Hamilton theorem, applications of Cayley-Hamilton theorem. Mostly 8 marks questions comes in exams. Verify Cayley-Hamilton theorem and find A inverse if it exists. Note one thing also, when you find characteristic equation, you have to check. You can check whether the characteristic equation is correct or not. As question is of 8 marks, if you check characteristic equation, then there are less chances of mistakes. If our characteristic equation is correct, then our question will be correct. For this, you have to check sum of diagonal elements, of given matrix A, of given matrix, say A, it should be equals to coefficient of lambda square. Coefficient of lambda square. You can this if it is cubic equation. This is for cubic equation. For cubic equation in lambda. If sum of diagonal elements of given matrix A is of 3 by 3 order. If sum of diagonal elements is equal to coefficient of lambda square, then your characteristic equation is correct, otherwise not. Or you can check determinant of A should be equal to constant term of characteristic equation. You can either check this or this. If these are satisfied, then our equation is correct. Characteristic equation is correct. So for Cayley-Hamilton theorem, first of all, you have to find characteristic equation, then solve determinant A minus lambda equals to 0, then put lambda equals to A, and we have to prove it is 0 matrix. If it comes out to be 0 matrix, then Cayley-Hamilton theorem is verified. See one example. Very, very important question. See one example. Very, very important. Verify Cayley Hamilton theorem for the matrix A equals to 2 1 1 2 1 1 0 1 0 0 1 0 and 1 1 2. Find A inverse if exists. We have to verify Cayley-Hamilton theorem. So, first of all, we will find characteristic equation. First of all, we will find characteristic equation. See how. For characteristic equation, we have to solve determinant of A minus lambda I equals to 0. How? Determinant of A minus lambda I. You know what is identity matrix? Diagonal elements of identity matrix are 1 and non-diagonal elements are 0. A matrix is 2, 1, 1, 0, 1, 0, 1, 1, 2, minus lambda I. Lambda and I. I is 1 0 0 0 1 0 0 0 1. Now you have to multiply this lambda with inside elements of determinant. What you will get? 2 1 1 0 1 0 1 1 2 and minus 1. You have to multiply lambda with inside elements. 1 into lambda is lambda, 0 into something 0, 0 into something 0, 0. Lambda into 1 is lambda, again 0, then 0, 0, lambda equals to 0. Next step is to subtract. So write down first column 2, 0, 1. Now minus first column of second matrix, minus lambda, minus 0, minus 0. Second column of first matrix, 1, 1, 1. Subtract second column of second matrix. What you will get? Minus 0, minus lambda, minus 0. Now write down third column of first matrix. What you will get? 1, 0, 2. Now subtract third column of second matrix. What you will get? Minus 0, minus 0 and minus lambda, and this should be equals to 0. Now simplify it. What you will get? 2 minus lambda, 1 minus 0, 1, 1 minus 0, 1. Then here it is 0, 1 minus lambda, again 0, again 1, 1 and 2 minus lambda equals to 0. Or there is a trick, you can directly write A minus lambda I equal to 0. How? Simply subtract lambda from diagonal elements. Simply subtract lambda from diagonal elements. What you will get? 2 minus lambda, 1 minus lambda and 2 minus lambda. And keep other non-diagonal elements as it is, like 0, 1, 1, 1, 1 and 0. These are non-diagonal terms or elements. For what is the trick for directly writing a minus lambda I equals to 0? Simply subtract lambda from diagonal elements of the given matrix A and you will directly get this determinant. Now, what is the next step? Next step is to solving the determinant. First step is write determinant of a minus lambda I equals to 0, and second step is solve the determinant a minus lambda I equals to 0. See how we solve determinant. We have to solve the determinant 2 minus lambda, then 1, then 1, then 0, 1 minus lambda, again 0. Third row is 1, 1 and 2 minus lambda. We have to simplify this determinant. See how. First of all, write first element. What you will get? 2 minus lambda. Now skip the row and column containing the element 2 minus lambda and write 2 by 2 order determinant. What you will get? 1 minus lambda, 0, 1 and 2 minus lambda. Next sign scheme is plus, minus, plus. So next term will be minus 1. Now skip the row and column containing this 1 and write the 2 by 2 order determinant. What you will get? 0, 0, 0, 0 and 1 and 2 minus lambda. 1 and 2 minus lambda. So plus, minus, plus. Next term will be plus 1 and write down 2 by 2 order determinant by skipping the row and column containing this one. What you will get? 0, 1 minus lambda, 0, 1 minus lambda, 1 and 1. Now we again simplifying it. 2 minus lambda is outside and opening this 2 by 2 order determinant. How? Multiply this with this. What you will get? 1 minus lambda and 2 minus lambda and subtract product of these two terms. We have to subtract 1 into 0. 1 into 0. Now next term minus 1 outside. Open this determinant. How? Multiply this into this. What you will get? 0 into 2 minus lambda. Then subtract product of these two terms. What you will get? 1 into 0. Now last is plus 1. Open the determinant. Product of these two terms. 0 into 1. You have to subtract product of these two terms. 1 and 1 minus lambda. And right hand side is 0. Again simplifying, 2 minus lambda outside. What we have inside? Multiply this one with this. What you will get? 2 minus lambda. Again multiply this minus lambda with these two terms. What you will get? Minus 2 lambda. Minus into minus is plus. Lambda into lambda is lambda square. Next term will be square bracket is not closing here. Here it is open bracket. Minus 1 into 0. 0 into something is 0. Now close the square bracket. Next term minus 1 into 0 into something 0 minus 0 into something 0. We can close square bracket over here. Next term is plus 1 into 0 into something. It is 0 minus. Minus is outside. Whenever there is minus sign outside the bracket and you have to open the bracket, simply change the sign. 1 is positive, write it as negative. Minus lambda negative, write it as positive. Close the square bracket and equals to 0. Now again simplify. Outside 2 minus lambda. What you will have inside? Write down higher power lambda square. Combine lambda terms minus lambda minus 2 lambda. It will be minus 3 lambda and plus 2 and minus 0. You can skip it because something minus 0 is something. Now minus 1 into 0. 0 minus 0. 0. 0 into something. 0. So we can write here minus 0. See how we write next term? Next term is plus 1. 0 minus 1. It is minus 1. And 1 into lambda. It is plus lambda and equals to 0. Again simplifying. Now multiply this 2 with this bracket. 2 into lambda square. 2 lambda square. 2 into minus 3 lambda. 3 to the 6. It is minus 6 lambda. Multiply this 2 with 2. What you will get? 4. Now multiply this minus lambda with this. What you will get? Minus lambda cube. As minus, so sign will interchange. Sign will get interchanged. If there is plus, write minus. If there is minus, convert it into plus. So here it is minus. You have to taken it as plus. Lambda into 3 lambda. You will get 3 lambda square. Minus lambda into 2. Minus 2 lambda. Minus 0 minus 1. Minus 1 and plus lambda equals to 0. Now write down highest power of lambda. As it is cubic equation, so highest power of lambda will be minus lambda cube. First term is minus lambda cube. Next you have to write lambda square. Here it is 2 lambda square. 2 plus 3, 5 lambda square. So what you will get? 5 lambda square. First of all, write lambda cube, then you have to write lambda square, and next to write lambda. Combine lambda terms. Minus 6 lambda minus 2 lambda. Minus 6 and minus 2. It will be minus 8. Minus 8 plus 1. It will be minus 7 lambda. And at last you have to write constant term. Here it is plus 4. 4 minus 1. It will be minus 3 equals to 0. This is our required characteristic equation. So characteristic equation is minus lambda cube plus 5 lambda square minus 7 lambda plus 3 equals to 0. This is our characteristic equation. You can verify. Check whether characteristic equation is correct or not. Check sum of diagonal elements. Sum of diagonal elements equals to coefficient of lambda square or determinant equals to constant term. Both conditions are satisfied over here. So our characteristic equation is correct. Now we verify Cayley-Hamilton theorem. How? For Cayley-Hamilton theorem, simply put lambda equals to A. You have to simply put lambda equals to A. First of all, write down by Cayley-Hamilton theorem. By Cayley-Hamilton theorem, put lambda equals to A in this equation. So lambda will become A. What you will get? Minus A cube. Put lambda equals to a, what you will get? Plus 5a square. Put lambda equal to a, we will get minus 7a. And we can't subtract constant term from matrix. We have to make or convert it into matrix. In like in constant, if we multiply 1 with any scalar, that scalar will not get affected. 3 into 1 is 3. Similarly, in matrices, if we multiply identity matrix with any constant, it will we can multiply in matrices uh, any scalar with identity matrix to convert that scalar into a matrix. So we multiply here 3 with identity and it is equals to 0, and we have to verify this equation, or we can take minus common, we can take minus common from here. What you will get? Take minus common from here. What you will get? A cube minus 5a square plus 7a plus 3i equals to 0. What you will get? A cube minus 5a square plus 7a. Here it is minus. Here it is plus 3. As plus 4 minus 1, it is plus 3. And here it is plus 3i, and here it is minus. Okay. As 4 minus 1 is 3. So plus 3i, and when you will take minus common, it will become minus 3i. Now we have to verify this equation. See how for its verification, you have to find the value of a square, a cube, and after finding the values of a square and a cube, substitute values in this equation and check whether it comes out to be 0 matrix. If it comes out to be 0 matrix, then our Cayley-Hamilton theorem is verified, otherwise not. See how we proceed now. Now we have to find the value of a square. See how we multiply two matrices. For a square, we have to multiply a matrix with a. We have to multiply matrix A with A. See how, what is the value of A matrix? It is 2, 1, 1 and 0, 1, 0, 0, 1, 0 and 1, 1, 2. This is our A matrix. It is given. We have to multiply this matrix with 2, 1, 1, 0, 1, 0, 1, 1, 2. We have to make 7. 7 means you have to multiply this row with this column first. Multiply it 2 into 2. 4. 1 into 0. 0. 1 into 1. It is 1. Now you have to multiply same row with second column. See how? 2 into 1. It is 2. 1 into 1. It is 1. 1 into 1. It is 1. Now you have to multiply same first row with third column. See how? 2 into 1. It is 2. 1 into 0. It is 0. And 1 into 2. It is 2. Now instead of first row, you have to take second row and you will get second row product matrix. But you have to multiply similarly, first by first column, then by second column, then by third column. See how? When you multiply second row with first column, 0 into 2, you will get 2. Add next product of next two terms, 1 into 0, it is 0. Product of next two terms, 0 into 1, it is 1. Similarly, you have to multiply second row with second column. See how? 0 into 1, it is 1. 1 into 1, it is 1. Again 0 into 1, it is 0. Here it is 0 as
Ma'am,
0 into here it is a 0 as 0 into something is 0, 0 into something is 0, 0 into something is 0. 0 into
okay.
something 0, 1 into 0, 0, 0 into 1, it is 0. Now 0 into 1, it is 0, 1 into 1, it is 1, 1 into 0, it is 0. Now multiply with third row, third column. 0 into 1, it is 0. 1 into 0, it is 0. Then 0 into 2, it is 0. Now instead of second row, you have to take third row. Third row with first column. 1 into 2, it is 2. Then 1 into 0, it is 0. Then 2 into 1, it is 2. Now third row with second column. 1 into 1, 1. 1 into 1, 1. 2 into 1, it is 2. Now third row with third column. 1 into 1, it is 1. 1 into 0, it is 0. And 2 into 2, it is 4. Now add these terms. What you will get? 4 plus 1, it is 5. 2 plus 1 plus 1, it is 4. 2 plus 2, it is 4. So first row is 5, 4, 4. See second row, 0, 1 and 0. So second row is 0, 1, 0. See third row, 2 plus 2, it is 4. 2 plus 1 plus 1, it is 4. And last, it is 5.
Hi.
This is the value of a square. So a square is 544, 010 and 445. Now we have to find the value of a cube, as a cube is required to verify Cayley-Hamilton theorem. How we will find a cube? Simply multiply a square with a. And what is the value of a square? It is 5, 4, 4 and 0, 1, 0, 4, 4 and 5. You have to multiply this a square with a matrix. And what is the value of a matrix? 2, 1, 1, 0, 1, 0 and 1, 1, 2. Again, we have to make it as 7. See how? First of all, multiply first row with first column. What you will get? 5 into 2, it is 10. Add second term with second. 4 into 0, it is 0. Third term with third term. 4 into 1, it is 4. Now multiply first row with second column. 5 into 1, it is 5. 4 into 1, it is 4. 4 into 1, it is 4. Again multiply first row with third column. 5 into 1, it is 5. 4 into 0, 0 into something is always 0. 4 into 2, it is 8. Now instead of first row, we have to multiply second row. Firstly by first column. How? 0 into something, it is 0. 1 into 0, it is 0. 0 into 1, it is 0. Now multiply second row with second column. How? 0 into 1, 0 plus 1 into 1, it is 1 plus 0 into 1, it is 0. Now multiply second row with third column. What you will get? 4 into 1. It is 4. Then 4 into 0. It is, no, second row. We have to multiply second row. 0 into 1. It is 0. 1 into 0. 0. 0 into 2. It is 0 into 2. It is 0. Now, instead of second row, take third row. Multiply third row with first column. So, 4 into 2, 8 plus 4 into 0, 0 plus 5 into 1, it is 5. Now, multiply it with second column instead of first. 4 into 1, 4 plus 4 into 1, 4 plus 5 into 1, 5. Now multiply it with third column. 4 into 1, 4 plus 4 into 0, 0 plus 5 into 2, it is 10. Now add it. 10 plus 4, it is 14. 5, 4, 3 are 12, 12 plus 1, 13. 5 and 8, it is 13. 0, it is 1, 0. MD Aslam, please mute yourself. Aslam. Eight plus 5, it is 13. 4, 4, 8, 8 and 5, 13, and it is 14. So we will get value of a cube as what? We get value of a cube. It is 14, 13, 13, 0, 1, 0, 13, 13, and 14. As we have find the value of a square and value of a cube, next step is substituting these values in left hand side of Cayley-Hamilton theorem. Simply substitute these values in left hand side of Cayley-Hamilton theorem. What is left hand side? We have a cube. Left hand side, it is a cube minus 5a square plus 7a, and we have minus 3i3 equals to 0. Now start substituting. First of all, value of a cube. We have find value of a cube as 14, 13, 13. And second row 0, 1 and 0. And third row we have 13, 13 and 14. Outside we have minus 5. Inside put the value of the matrix A square. What you have the value of A square? 5, 4, 4. What is second row? Second row is 0, 1, 0. 0, 1, 0. And for third row, you have 4, 4, 5. 4, 4, 5. Now plus 7 into A. Substitute the value of A matrix. A matrix is 2, 1, 1, 2, 1, 1. Then 0, 1, 0. 0, 1, 0, and it is 1, 1, 2. 1, 1, 2. Now, as we have taken only left hand side, so 0 should not be there. As we have taken only left hand side of the Cayley-Hamilton theorem to verify it. Minus 3 and 3 by 3 order identity matrix. What it will be? 1 0 0 0 1 0 0 0 1. We have to write 1 on diagonal elements and 0 on non-diagonal element. Next step is to simplify it, solve it, and you have to show it is equal to 0 matrix. How we solve it? Simply write first column of first matrix. First column of first matrix. What you will get? 14, 0, 13. Now write first column of second matrix with multiply it minus 5. Minus 5 into minus 5. Minus 25 minus 0 and minus 20. Now first column of next matrix multiply with 7. What you will get? Plus 14 plus 0 and plus 7. Now write her first column of last matrix with multiply it with minus 3. What you will get? Minus 3 minus 0 and minus 0. Now write second column of every matrix. Second column. What you will get? 13 1 13. Now multiply minus 5 with this column. What you will get? 5 into 4 20. 5 into 1 5. 5 into 4 20. Now multiply this column with 7. We will get plus 7 and plus 7. Now multiply minus 3 with this column and write over here. We will get minus 0, minus 3 and minus 0. Now write third column. Third column of first matrix is 13, 0, 14. Third column of second matrix, it is minus 20, minus 0, minus 20. Third column of third matrix, multiply with 7. It is plus 7, 0 into 7. It will be 0, 7 to the 14. Now third column, multiply with minus 3. Third column, multiply with minus 3. What you will get? Minus 0, minus 0 and plus 3. And it must be equals to 0. If it is not 0, then some mistake is there. Now see, minus 25 and minus 3. Minus 28, 14 plus 14, 28. 28 minus 28, 0. 13 plus 7, 20, 20 minus 20, 0. 13 plus 7, 20, 20 minus 20, it is 0. It is 0. 1 plus 7, 8. Minus 5, minus 3, minus 8. 8 minus 8, 0. Again, 0. 13 plus 7, 20, 20 minus 20, it is 0. 13 plus 7, 20, 20 minus 20 is 0. 14 plus 14. See, I think here it is some mistake. 5 into 5, it should be minus 25. Your answer always comes out to be 0. If it is not 0, check where is your mistake. You have to check it. As I have wrongly written here 20, but here it is 25 as no, this is second column. Second column means second matrix. 5 into 5 is 25. Now check. Again there is some mistake as it is not 0. Minus 3 into 1. Here it should be minus 3. Here it should be minus 3. Similarly, if your term is not comes out to be 0, please check it. Don't write here non-zero term. 14 into 14 plus 14, 28. Minus 25 minus 3, minus 28. 28 minus 28, it is 0. So always your answer will comes out to be 0, always. So it is 0 equals to right hand side. Therefore, Cayley's Hamilton theorem is verified. If some students have problems in derivatives and integral, then you have to learn this method or practice this method as no derivatives involved, no integrals involved. Simply we have to multiply matrices and subtract or add matrices. This is very easy topic, and 8 marks questions always comes from this topic. Now, one more part of this question is find A inverse if exists. And what are the steps I have told you? You have to multiply A inverse with the left hand side of Cayley-Hamilton theorem. You have to multiply with A inverse. So suppose let this equation be A. Suppose this equation is first equals to 0. It is first equation. Let this equation be first, not A. First equation. Now for A inverse. Now what are our steps for solving A inverse? See how. For A inverse, multiply equation 1 with A inverse. Multiply. See how. Write down A inverse and the whole equation. A cube minus 5A square plus 7A minus 3I3 and equals to. If you multiply A inverse with 0, it is 0. 0 into something is 0. So it will be 0. Now A cube, A inverse is 1 over A. A cube upon A, it is A square. A square upon A, it is A. A upon A, it is identity. If you divide matrix with matrix, answer should be in matrix, not scalar. Minus 3 into I3 into A inverse, it will be A inverse and equals to 0. I have told you previously, for finding A inverse, keep A inverse term on left hand side and take rest of the terms on right hand side. Keep A inverse term on left hand side and you have to take all other terms on right hand side. See how? Here it is minus 3A inverse. Or you can take this negative term on right hand side so that it will become positive. If I take minus 3A inverse on right hand side, what I will get? 3A inverse. So what are the remaining terms? A square minus 5A plus 7I equals 7I. 3A inverse is A square minus 5A plus 7I. Now what will be A inverse? 3, here it is multiply. When you take 3 from left hand side to right hand side, multiplication will change into division. It will become 1 by 3 into A square minus 5A plus 7I. Now we know the value of A square, we know the value of A, we know the value of identity. Simply put all values in this equation and simplify it and you will get the required result. I am going to launch one poll. I am going to launch one poll. So do it. Now see how we find A inverse. See how we solve A inverse. Uh, for A inverse, we have to find the value of A inverse equals to 1 by 3 into A square minus 5A plus 7I. Now, on substituting the value of A square, A and identity in this equation, we have already solved the value of A square. So no need to find the value of A square again, as we have the value of A inverse. For A inverse, we have to solve 1 by 3 into A square minus 5A plus 7I3 E 7I3. Now substituting the values, A inverse is 1 by 3 is outside. Substitute the value of the matrix A square. A square is 5, 4, 4, 5, then 0, 1, 0, 0, 1, 0, and third row is 4, 4, 5, 4, 4, 5, minus 5. Here it is matrix. Substitute the value of A matrix. It is 2, 1, 1, 2, 1, 1, then 0, 1, 0, 0, 1, 0, and 1, 1, 2. Now substitute the value of identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Now write the column matrix first. First column, it is 5, 0, and 4. Multiply 5 with first column. What you will get? Minus 10, minus 0, and minus 5. Multiply 7 with this column. What you will get? Plus 7, plus 0, plus 0. Now second column. 4, 1, 4. Don't multiply 3 with this matrix. As 1 by 3, don't divide 3 with this matrix, as 1 by 3 is outside the simplification of the whole matrices. So first of all, you have to simplify the given matrices and make it a single matrix, and when you will get single matrix, then divide each element of that matrix with 3. See how here it is second column. Multiply it with minus 5, minus 5, minus 5, minus 5. Multiply this column with 7, plus 0, plus 7, plus 0. Now write third column of first matrix 4, 0, 5. Multiply third column with minus 5, minus 5, minus 0, and minus 10. Multiply 7 with third column. You will get 0, 0, and 7. Now do its simplification. See how 5 plus 7, it is 12, and 12 minus 10, it is 2. 4 minus 5, minus 1. 4 minus 5, minus 1. It is 0. 7 plus 1, 8. 8 minus 5, minus 3. 0 and minus 1, minus 1. 7 and 5, 12. 12 minus 10, 2. So what you will get? A inverse, you will get 2 minus 1 minus 1, 0, 3, 0 minus 3. See 7 plus 1, 8, 8 minus 5, it is 3. So 0, 3, 0, and in last minus 1, and 2. So you write therefore A inverse equals to 1 by 3, 2 minus 1 minus 1, 0, 3, 0, minus 1 minus 1, and 2. This is your answer. I am taking one more example, very important example based on application of Cayley's Hamilton theorem. See how. See one more example which is based on application of Cayley-Hamilton theorem. I am going to take one more example. Find characteristic equation of the matrix A. Second is find the characteristic equation of the matrix. This is very important question. Very important. I am taking same matrix as I have taken in previous example. Matrix A equals to 2 1 1 2 1 1 0 1 0 and 1 1 2. This is our A matrix, and hence find the matrix and hence find the matrix represented by a raised to power 8 minus 5 a raised to power 7 plus 7 a raised to power 6 minus 3 a raised to power 5 plus a raised to power 4 minus 5 a raised to power 3 plus 8 a square minus 2a plus I3. I3 means 3 by 3 order identity matrix. See what is the statement? Find characteristic equation of the matrix. Characteristic equation means you have to find the determinant of a minus lambda I equals to 0 and then put lambda equals to a, and as every square matrix satisfies every square matrix satisfies every square matrix satisfies its characteristic equation. So the equation which comes in lambda, we put lambda equals to a and we get, as it is 3 by 3 order matrix, we get cubic equation in A. And suppose that equation as first equation, and with the help of that equation you have to simplify it. If you don't use Cayley-Hamilton theorem over here, it's very difficult to find the value of a raised to power 8, a raised to power 7, a raised to power 6 in 8 marks question. It's not difficult, but it is time consuming. To save your time for 8 marks question in exam, we use Cayley-Hamilton theorem. So Cayley-Hamilton theorem states every square matrix non-singular satisfies its characteristic equation. So our first step is to find characteristic equation. As I have taken same matrix as in previous example, so I directly write the value of characteristic equation. As we find characteristic equation in previous matrix and we have find the values of a square, a cube also in previous example. So I am directly writing the here it is determinant of a minus lambda I equals to 0 for characteristic equation. As our first step is to find characteristic equation. We have solved this characteristic equation in previous example, so I am directly writing over here. It is minus lambda cube plus 5 lambda square minus 7 lambda plus 3 equals to 0. And you have to check whether your characteristic equation is correct or not. I have told you two methods to sum of diagonal elements or with the determinant. If sum of diagonal elements equals to coefficient of lambda square or determinant equals to constant term. Now for by Cayley-Hamilton theorem, next step is by Cayley's Hamilton theorem. This step is already done in previous example, so I am directly writing the equation with taking minus sign common. It is a cube minus 5a square plus 7a minus 3I equals to 0. As I have told you the steps for application of Cayley-Hamilton theorem, you have to consider this equation as equation number 1. As we have to use this equation to simplify equation with power 8. To simplify equation with power 8. See how. Now consider the equation given in the statement. Now you have to find the value of a raised to power 8, a raised to power 8 minus 5a raised to power 7 plus 7a raised to power 6 minus 3a raised to power 5 plus a raised to power 4 plus a raised to power 4, then minus 5a cube plus 8a square plus 8a square minus 2a and plus I. We have to represent this equation in matrix. We have to represent this equation in matrix. One way is find the value of a raised to power 8, a raised to power 7, a raised to power 6, a raised to power 5, a raised to power 4 and substitute all these values in this equation and simplify, add, subtract matrices, and it is very time consuming method. So we don't go with it. We don't go with this method. We use application of Cayley-Hamilton theorem. We use this equation. This equation is with the help, we have find this equation with the help of Cayley-Hamilton theorem. We are using this equation over here. See, for this, you have to compare the coefficients 1, 5, 7, 3. Here it is 1, 5, 7, 3. But inside you have to make coefficient a cube. So if you take a raised to power 5 common from here, if you take a raised to power 5 common from here, you can write equal to here. On taking a raised to power 5 common from these terms, what you will get? A cube minus 5a square plus 7a minus 3I. If you take a raised to power 5 common from first 4 terms, what you will get? This equation. And it matches with left hand side of first equation and it is right hand side is 0. So this equation will become 0 and we have made first four terms zero with the application of Cayley-Hamilton theorem. Now we have to make some adjustment again. Here it is 1, 5, 7, 3. Here it is 1. You have to compare only coefficients. You have to compare coefficients. If coefficients are not matching, you have to do some adjustments. You have to do some adjustment to make it equal, so that you have to make adjustments so that we can apply first equation in this. We can apply first equation in this. Or if there is confusion, you can write all the terms as it is first. For overcome confusion, write this. Now this is 0, this is 0, 0 into something 0. Now we have to make equation first in other terms. But in next terms, we have coefficients 1, 5. But instead of 7, we have 8. Instead of 7, we have 8. See, we have here 7, but we have here 8. We can write, or we can split 8a square into 7a square plus a square. See how? Write down other terms as it is: a raised to power 4 plus 5a cube, here it is minus, plus 8a square minus 2a and plus I. Now see how we do adjustment. 0 into something is 0. If I am taking, for making a raised to power 4 as a cube, we have to take a common. A common. Here it is 0. 0 into something is 0. Take a common. What we need? A cube. Then minus 5a cube, minus 5a square. A is common. It is minus 5a square. Matched. This term matched. Next, we want plus 7a to apply to use this equation. But here it is 8, but I want 7. So simply write 7. Okay. Next it is minus 3 or minus 3. Here it is minus 2. Minus 3a. If a is taken or you can skip this. We do adjustment only in 3 terms. Here it is 7a square, but we have 8a square, so we have to add a square, as 7a square plus a square is 8a square. Now write other terms as it is: minus 2a plus I. What we have done, we have simply take a as common from next 3 terms. When we take a common, instead of 7 we have 8. We split 8 into 7a and 7a square plus a square. Now see from equation first. What is the value of this equation? What is the value of this equation? Minus 3i on right hand side. When you take this on right hand side, what it will become? Plus 3. By first equation, it is 3i. By equation first, it is 3i. And write other terms as it is: a square minus 2a plus I. Simplify it. Identity into matrix is matrix a into 3. It is 3a plus a square minus 2a plus I. Write highest coefficient first. It is a square. 3a minus 2a. It is a and plus I. So after simplification, what we will get: a square plus a plus I. Now when the equation becomes less than 3, power of a becomes less than 3, substitute the value of the matrices and simplify it. What is the value of a square? In first example, in previous example, we have find its value as 544, 5 4 4 0 1 1 0 1 1 and 4 4 5 4 4 5 plus A. A is given matrix and given matrix is 2 1 1 2 1 1 and 0 1 0 0 1 0 and 1 1 2 1 1 2 and plus I. Identity matrix diagonal elements 1 1 0 0 0 1 0 0 0 1. Now add it in column wise. First column 5 0 4. First column of second matrix 2 0 1 2 0 1. First column of third matrix 1 0 0 1 0 0. Now write down second column. Second column is 4 1 5. Second column of second matrix 1 1 1 1 1 1. Second column of third matrix 0 1 0 0 1 and 0. Now write down third column. It is 4 1 5. Now write down third column of second matrix 1 0 2 1 0 and 2. And third column 0 0 1 0 0 and 1. Simplify it. What you will get? 5 plus 2 7, 7 plus 1 it is 8. 4 plus 1 it is 5. 4 plus 1 it is 5. 0 3 1 5 6 and 8. So the answer is 8550355. Here it is 4. Here it is 4. Make one correction. So this is 5. And see now. Sorry, the value of A square matrix here it is 0. Here it is 0. So here it is 0 value of A square. So it is 0. Now it is correct answer. You can check the values of matrix A square. So the answer is 855, 030 and 558. Now I am going to launch one poll. Do it. Poll is on your screen. Time is 1 minute. Now see again, very important question. Apply Cayley-Hamilton theorem. Apply Cayley-Hamilton theorem to A equals to A matrix is 1, 2, 2 minus 1. 1, 2 and 2 minus 1. This is given matrix. And deduce that A raised to power 8 equals to 625 into identity matrix. Deduction means you have to prove it with the result which you have find in the question. As Cayley-Hamilton theorem, from Cayley-Hamilton theorem we will find equation. It is of 2 by 2 order matrix, so we will find when we use a characteristic equation, we will get a quadratic in lambda. We will get quadratic in lambda by Cayley-Hamilton theorem. What we will get? We have to put lambda equals to A. We will get A square, value of A square, and using that, suppose that equation as first equation, and using that equation we have to find deduce means using that result, using that equation, we have to we have to prove this thing. We have to prove this thing using that equation. Now first step is always in Cayley-Hamilton theorems, first step is for characteristic equation. For characteristic equation, determinant of A minus lambda I equals to 0. We know how to write directly this determinant. Simply subtract lambda from diagonal elements. I will get 1 minus lambda into 2, then 2 into minus 1 minus lambda, and equate it equals to 0. As it is equation, so equal sign will be there. Now open this determinant, multiply this factor with this term with this term. What you will get? 1 minus lambda into minus 1 minus lambda. Now subtract product of these two terms. 2 into 2, it is 4 and equals to 0. Now you have to simplify it. See how. Multiply this one with this equation. We will get minus 1 minus lambda. Now multiply minus lambda with this equation. What you will get? Plus lambda square minus 4 equals to 0. First of all, write down higher power of lambda. It is lambda square. Then lambda minus lambda plus lambda will get cancelled out. Minus 1 and minus 4, it is minus 5 equals to 0. This is our required characteristic equation. So characteristic equation is lambda square minus 5 equals to 0. In Cayley-Hamilton theorem, after this step, you have to apply Cayley-Hamilton theorem. So write down by Cayley's Hamilton theorem, by Cayley-Hamilton theorem. Put lambda equals to A. Why? Because according to Cayley-Hamilton theorem, every square matrix non-singular satisfies its characteristic equation, and this is characteristic equation. So A matrix satisfies this equation. So what we will get, a square minus 5i. I told you with scalar, this is matrix and you can subtract matrix from matrix. So you have to convert this scalar into matrix by simply multiplying identity matrix of same order. Here A is of 2 order. So identity matrix must be of order 2 and this is equals to 0. So we use Cayley-Hamilton theorem over here. Now from this equation we have to deduce this equation. See here a term is on left side, identity term is on right side. So according to statement we can write it as a square equals to 5 times identity. Now what we need, a raised to power 8. We want a raised to power 8 instead of a square. So what we will do, square both sides. Simply square both sides. On squaring, on squaring, a square is a square. A square, a square of a square is a raised to power 4. Or you can write it like a square whole square 5i whole square. Now here 2 into 2 powers get multiplied. We will get a raised to power 4. 5 into 5, 5 square is 25. Square of identity matrix is always identity matrix. As in scalars, 1 into 1 is 1. In matrices, identity into identity is again identity. So it is this. But instead of a raised to power 4, I want a raised to power 8. So what we need to do? Again squaring. Again squaring on both sides. Do squaring. A raised to power 4 into squaring. Do squaring. Here it is square. Here it is square. It implies a raised to power 8. Powers get multiplied. 25 square. It is 625i. Because I square is again I and hence deduced. Hence deduced. I am going to share one poll on your screen. Time is 1 minute. Do it. Time is 1 minute. I am going to stop the poll. Again, see one very important question. Verify Cayley-Hamilton theorem for verify Cayley-Hamilton theorem for the matrix A equals to, given matrix is 1 4 2 3. 1 4 2 3. Find A inverse and also express express a raised to power 5 minus 4 a raised to power 4 minus 7a cube plus 11a square minus a minus 10i minus a minus 10i as a linear polynomial in A. As a linear polynomial in A. For verification of Cayley-Hamilton theorem, you know the first step. First step is to find characteristic equation. For characteristic you have to solve the determinant. Do one pole. Do it. For characteristic equation, determinant of A minus lambda I equals to 0. Last 20 seconds. Do it fast. I am going to stop the poll. Last 10 seconds. For characteristic equation, we have to solve the determinant A minus lambda I equals to 0. We can write directly this determinant simply by subtracting lambda from diagonal elements. See how? 1 minus lambda, 4, 2, 3 minus lambda equals to 0. Now we have to solve this determinant. See, multiply it with this. What you will get? 1 minus lambda into 3 minus lambda minus. Multiply 2 with 4. What you will get? 2 into 4 is 8 equals to 0. Simplify it. Multiply 1 with this equation. You will get 3 minus lambda. On multiplying minus lambda with this equation, you will get minus 3 lambda plus lambda square. Here it is minus 8 equals to 0. First of all, write higher power of lambda. It is lambda square. Then lambda minus 3 lambda. It will be minus 4 lambda. 3 minus 8. It will be minus 5 equals to 0. So our required characteristic equation is lambda square minus 4 lambda minus 5 equals to 0. For the verification of Cayley-Hamilton theorem, we have to prove that put lambda equals to A. We have to prove that A square minus 4A minus 5I equals to 0. We have to prove the equation number 1. We have to prove the equation A square minus 4I minus 5I equals to 0. Now we have the value of A and I, but we don't have the value of A square. So we find its value A square. Multiply matrix A with A. 1, 4, 2, 3. Multiply it with 1, 4, 2, 3. Multiply first row with first column. 1 into 1 is 1. 4 into 2 is 8. Multiply first row with second column. 1 into 4 is 4. 1 into 4 is 4 and 4 into 3 is 12. Now instead of first row, you have to multiply second row with first column. 2 into 1, 2, 3 into 2, 6. Now multiply second row with second column. 4 into 2, 8. 3 into 3, it is 9. Simplify it. 8 plus 1, 9. 12 plus 4, 16. 6 plus 2, 8. 8 plus 9, 17. So the value of matrix A square comes out to be 9, 16, 8 and 17. Simply put, value of A square A and identity in equation number 1. When you put the values, we will get equation number first is A square minus 4a minus 5i equals to 0, implies value of a square is 9, 14, 9, 14, 8 and 17 minus 4a. Value of A matrix is 1, 4, 2 and 3 minus 5i. Identity matrix is 1, 0, 0, 1. And we have to prove it as 0. Now, first column 9, 8. Write down second column. Second column is minus 4. Sorry, first column of second matrix. First column of second matrix. It will become minus 4 minus 8. First column of third matrix minus 5 and minus 0. Now second column, it is 14, 17. Second column of second matrix, 4 into 4, 16. 4 into 3, 12. Second column of third matrix, minus 0, minus 5. And we have to prove it as 0. On doing simplification, we will check whether it comes out to be 0 or not. If it is not 0, then there is some mistake and we have to remove or check that mistake. See, 9 minus 4 minus 5 minus 9, 9 minus 9, 0. See, here it is mistake as 14 minus 16. 14 minus, check the value of matrix A square. Value of A square. Here it is 16, not 14. 16. So 16 minus 16, it is 0. And 8 minus 8, 0. 12 and 5, 17. 17 minus 17, 0. If all elements of matrix are 0, then it is a 0 matrix. Hence, Cayley-Hamilton theorem verified. Now there is one more part of the question. Consider the statement given in the question: a raised to power 5 minus 4, a raised to power 4 minus 7a cube, or you can write over here. Suppose this equation is your first equation, and consider a raised to power 5 minus 4, a raised to power 4 minus 7 a cube, then plus 11 a square minus 11 a square, then minus a and minus 10i. Minus a and minus 10i. What we have to do? We have to express the given this equation as a linear polynomial in A. As a linear polynomial in A. So what we have to do? Compare the coefficients with equation number 1. Compare the coefficients. Here we have 1 minus 4 minus 5. 1 minus 4 and minus 7. We can split minus 7a cube as we can write it as minus 5a cube and minus 2a cube. So on taking a cube common, what we will get? A square. Simply write this equation: a square minus 4a minus 5. Now you can check a cube into a square. It is a raised to power 5. A cube into minus 4a. It is minus 4a4. A cube into minus 5i. It is minus 5a cube. But we have minus 7. So we have to write minus 2a cube. 7a cube is minus 5a cube and minus 2a cube. Now write remaining terms. Plus 11a squared minus a minus 10i. From equation number 1, its value is 0. So it is a cube into 0. And what you will get? Minus 2 plus 11. It is minus 9a squared. No, plus 11 minus 2. It is plus 9a squared minus a minus 10i. 0 into something. See from first equation. 0 into something is 0. Okay, do one poll. Poll is on your screen. Do it. Last 30 seconds. I am going to stop the poll. Do it fast. Hurry up, students. I am going to stop the poll. See students, 0 into some, here from equation we put the value 0 and we are left with minus 2a cube plus 11a square minus a and minus 10i. And we have to convert this equation in linear polynomial. Now 0 into something is 0. Now we want here a square. So take minus 2a common from here and directly write this equation. Directly write this equation: a square minus 4a plus 5i. Directly write first equation. Now open the bracket and do adjustments. It is minus 2a cube. Minus 2a cube match with minus 2a cube. Next, minus 4 into minus 2. Minus minus plus, it is 8a square. 8a square. But we have here 11. So 8 plus 3, a square. This is adjustment. 8a square and 3a square, it will become 11a square. Now again open the bracket. Minus 2a into plus 5. 5 into 2 minus 10a. Here we have write minus 10a. But we have only minus a. So for adjustment, write plus 9a. As minus 10a plus 9a minus 10a plus 9a will become minus a. Now multiply. Sorry, this is a square term. This is a square term. A square term we have already solved. See once again. See what we have done. Minus 2a into minus 4a. It is 8a square and we have 11. So we do adjustment 8, 9, 10, 11, 3a square. This part is done. Now 5 into 2 minus 10a. Minus 10a. But here we have minus a. So minus 10a plus 9a. It is minus a. We are only left with minus 10i. Now from equation number 1, value of this bracket is 0 minus 2a into 0. And we are left with plus 3a square plus 9a minus 10i. But we want linear equation. So what we will do? Do one more poll. Do it. I am going to end the poll. See students, in first equation we have minus instead of plus. Here it is minus. And when you multiply minus 2 with minus 5, you will get plus 10a. But here we have minus a. So if we write it as minus 11a, 10a minus 11a is minus a. So here it will be minus 11a. Make one correction. Here it is minus sign in equation number 1. So what we get? We get 3a square minus 11a minus 10i equals to 0. But we have to express the given equation as a linear polynomial in a. For that, here it is a square. So 0 into something 0, 0 minus 0, 0. Here it is 0. So take 3 common from here. And what you will get? A square. In first equation, it is a square minus 4a minus 5i. Okay. So write down first equation, a square minus 4a minus 5i. Now do adjustments. Open the bracket. Here it is equal to open the bracket 3a square matched, then 3 into 4, 12 minus 12a. It is minus 12a. But we have minus 11. If we add plus a minus 12a plus a, then it will become minus 11. Okay, now 5 into 3, it is minus 15i. Minus 15i, but here we have minus 10i. So we have to add 5i so that we will get plus 10i. So here we can write plus 5i. Now again using equation number 1, it is 3 into 0. 0 plus 3 into 0 plus a plus 5a. 0 into something, 0. So 0 plus 0 is 0 and a plus 5i, which is required result we want, which is you can write at last, which is linear polynomial in A. So if we want to write some equation in linear polynomial in A, first of all find characteristic equation of the given matrix. It will come equation in lambda, and by using Cayley-Hamilton theorem, put lambda equals to A, you will get equation in A. Suppose that equation as first equation, and if you want to find A inverse, multiply that equation with A inverse, and then take A inverse term on left hand side, keep it on left hand side, keep A inverse term on left hand side, and take rest of the terms on right hand side. If you don't have the value of a square, a cube, find the values and substitute the values and simplify a inverse. And if you want to express polynomial with power more than 1, like a raised to power 8, a raised to power 7, and you have to convert it into linear polynomial, then suppose the Cayley-Hamilton theorem equation, the equation which we find by with the help of Cayley-Hamilton theorem, suppose that equation as the equation number 1, and using that equation try to make adjustment and reduce slowly that equation in equation which you want as a linear equation. This is the way to express given equation in linear equation. I am going to launch one more poll. Last poll. Do it. I am going to end the poll. Next is diagonalizable matrices. Sometimes question came question will come from this topic. Topic is diagonalizable matrix. As clear from its name, it is diagonal matrix. A matrix A is said to be diagonalizable if there exists an invertible matrix B such that B inverse A into B equals to D. For 2 marks questions, you know the eigenvalues, you know how to find the eigenvalues. Simply write eigenvalues on diagonal elements and write non-diagonal elements as 0, and this is your diagonal or diagonalizable matrix. If your all eigenvalues are different, then your matrix will be 100% diagonalizable. Then your matrix will be 100% diagonalizable. There is a one result. A square matrix of order n is diagonalizable if and only if it has n linear independent eigenvectors. Matrix of order n is diagonalizable if and only if it has linear independent n linear independent eigenvectors. Note the matrix B which diagonalizes A is called modal matrix of A. B is model matrix. B is model matrix. You know diagonal matrix like A, B, C, and here 0. This is diagonal matrix. You know upper triangular matrix. If upper triangular entries are non-zero and these three are 0, it is called upper triangular matrix. Lower triangular matrix, if in some matrix lower triangular entries are non-zero, maybe some maybe 1 or 2, maybe 0. Lower triangular entries of lower triangular are non-zero, but here it must be, these three terms must be 0 in case of 3 by 3 order matrix. In diagonalizable matrix, we have B inverse A into B equal to D. Also, A equals to B, D, B inverse. Also, A equals to B, D, B inverse. You know what is D? D is diagonalizable matrix. D is your diagonalizable matrix. If D is diagonal matrix of order n, if D is diagonal matrix of order n, then we have its quadratic form. We can write it mainly in diagonal matrix. Simply you find eigenvalues and write those eigenvalues on diagonal elements and write non-zero. Actually, it is very lengthy question, but in your syllabus, 2 marks questions sometimes ask or statement of diagonalizable matrix. Actually, first of all, you have to find eigenvalues, then eigenvectors, then for diagonalizable, you have to find uh, uh, that eigenvectors in matrix B, then B inverse, then multiply B inverse with A, then multiply B inverse A into B, and what you will get D. It is very lengthy question, and in 8 marks in your syllabus, this question is only asked in 2 marks. For 8 marks, this is very lengthy question, but in your syllabus you have to do it for 2 marks. So simply write eigenvalues on your diagonal elements.